Good morning, everyone. This is Charles Ely, and welcome to the eighth of our vetting seminars on COMNET modeling guidelines and procedures. Um, this one is going to cover just one section, section 6.4 on space uses. Um, we've already covered the first five chapters, and now we're focusing on chapter 6. This is a very important section because many of the COMNET innovations are included in this section. Next week, I'm going to miss the next 2 weeks because I've got some travel plans. But John Arendt will pick up for me and cover envelope and begin the HVAC discussion, and I'll return on September 22nd. Um, Space uses are divided into these 8 categories. And what I've done is I've created a little gray box on the right side and highlighted the section from the MGP that we're talking about. So this will show up on most or all of the slides, and you can follow along. Um, Basically, a thermal block, which we covered last week, can encompass one or more HVAC zones, and an HVAC zone can encompass one or more spaces. And it's really at the space level where much of the model specifications are entered. Things like lighting, occupancy, and many other building descriptors are defined at the space level and then summed up at the thermal block level. Starting with general information, there's two areas. The first is the classification of the space, and this is very important. This applies when the building is being modeled using one of the space-by-space methods, as opposed to the whole building method. And basically, the modeler chooses or makes a selection from Appendix B of the modeling guidelines and procedures. Once this selection is made from Appendix B, then default values and baseline building conditions are then established. The other general information building descriptor is the floor area of the space. This has to be entered. It's mandatory. And so it's the conditioned floor area associated with the space, or maybe unconditioned if the space is unconditioned. And it's the thermal block then sums the areas of each space to calculate the area of the thermal block. This is an image of Appendix B. It has all of the different whole building categories and space-by-space classifications listed as rows, and the columns show the baseline building lighting power, receptacle values for plug loads, coefficients, which we'll get into in a few moments, occupancy levels and heat generated by occupants, outside air, water heating process, and also schedule references. This appendix is the categories here are all consistent with both California and ASHRAE 90.1 2001 and also 2007. So this table incorporates all of those data. Moving on to occupants, there are basically 3 building descriptors associated with occupants: the number of occupants, the heat rate associated with the occupant, both latent and sensible, and a schedule. These of course affect internal heat gain in the space, which will affect the balance point temperature and many other factors. When the HVAC simulation is performed, these data could also affect outside air requirements if technologies like uh, carbon dioxide sensors are being modeled. Moving on to interior lighting, which is a big part of the space section. The building descriptors include regulated lighting power. This is the lighting power for general purposes, which is covered by the scope of 90.1. There's also the user also has to enter the non-regulated lighting power. This is a this are things like lights over dental chairs and grow lights and things like this that are exempt from 90.1, and they show up equally in both the baseline building and the rated building. There's the lighting schedules, of course, and then retail display lighting has to be entered separately because this is treated as a use it or lose it allowance in 90.1, both 2001 and 2007. Decorative lighting power is also a use it or lose it allowance, up to 1 watt per square foot. So that has to be entered separately at each space. And both retail and decorative lighting will show up as the same value in both the baseline and the proposed building, up to the maximum amount. And then 90.1 2001 has another special allocation for VDT viewing, video display terminals. This was actually eliminated in later versions of 90.1, but since it's still in 2001 and we're supporting tax credits which reference 2001, we need to know this information. Then there's the light heat gain distribution. This is where heat from the lighting fixtures go into plenums, into the space itself, how much is radiation, and so forth. And then there's the power adjustment factors. The baseline building lighting, interior lighting, is determined mainly from the space classification. This sets the lighting power density for the baseline building. It's also determined from the presence of these use it or lose it allowances for retail display, decorative lighting, and VDTs. And the schedule for the baseline building is neutral dependent, which means it's the same as the rated building, except for possible daylighting adjustments, which we'll cover in just a moment. The light heat gain distribution is one of the inputs. This table is from the ASHRAE Handbook of Fundamentals and included in COMNET. It gives a range of heat that's delivered to the space. What's not delivered to the space would be delivered to the plenum above, and we've chosen a default as at the midpoint of the range. The power adjustment factors are credits that are allowed for automatic lighting controls, which are not already required by the baseline standard. This particular table, which is reproduced in COMNET, is table 3.2, table G 3.2 from the performance rating method. Moving on to daylighting controls, the first building descriptor, which is a very important one, is the daylight modeling method. And COMNET specifically recognizes two methods, but the second one has a couple of variations. The first method is an internal daylight model, such as that contained in DOE2, where all the calculations are done at the time step of the simulation. The second broad method is what we call an external daylighting model. This would be a case where the modeler would use a tool like Radiance or Spot and do some out-of-the-box calculations, and then come back into the hourly simulator with either schedule adjustments or a daylight ratio. We also recognize a couple of variants on the daylight ratio method. One is a modified daylight factor method, and the other one is a more detailed model where the sky is divided into patches, and there's essentially a daylight factor for each patch of the sky, and they're all added up for the daylighted space. And there's also language that allows other daylighting modeling methods to be used if they're supported by the simulator. The second building descriptor under daylighting that I'll talk about are the daylighting schedules. This is only applicable when the external model method is used and adjustments are made to the schedules. And so this would be the schedule you'd use for the daylighted spaces, and the default or the normal schedule would be used for non-daylighted spaces. The daylight ratios are a building descriptor. Now this is what we call a data structure in COMNET, because it's not just one value, but it could be an array of values or a whole system of values built around either the modified daylight factor method or the sky patch method. And then the daylighted area is important because not all of the space might be, only a portion of the space might be daylighted. And then continuing with the building descriptors, if either the internal daylight model is used or the daylight ratio methods are used, then these building descriptors are triggered. The first one is the reference position for illuminance calculations. The second one is the illuminance set point. This is the illuminance level that we're trying to achieve by the combination of daylighting and electric lighting. There's an input called fraction of controlled lighting. This would be the fraction of the lighting watts in the space that are controlled by the daylighting sensor. And then there's information about the daylighting control type. If it's a dimming control, then we need to know the minimum dimming power fraction and the minimum dimming light fraction. If it's a stepped control, we need to know the number of control steps and the step dimming control points. This is an example of a stepped control device with the horizontal axis is the foot candles of illumination that are provided, and the vertical axis is the fraction of the rated power of the lighting that's actually on. So you can see that as the illumination level from daylighting increases, the lighting system gradually shuts down. There's a similar graph here that shows dimming controls, and you can see that at some point, in this case at about 20 foot candles, the lights are full bright, and then they gradually dim down to about 30% of power in this case. But these are inputs that the modelers put into the model. Okay, so that's lighting and daylighting. Moving on to receptacles, this is one of the areas where I think COMNET has made some innovations. There's basically just two building descriptors. The first one is the receptacle power, and the second one is the schedule that's associated with that power. But there's three methods that COMNET has developed for developing the lighting power. The first method is it's a simple watts per square foot number that you can pull from Appendix B and use. When you do that, that number gets used in both the rated building and the baseline building, so there's no credit. If you have detailed information about the number of computers and copy machines and so forth, then you can actually calculate the receptacle power using equations 4 and 5, which we'll cover in just a moment. And then the third method, if you have both detailed information and the building owner is willing to make a long-term commitment to purchase Energy Star equipment, then the equipment power in the rated building can be reduced. And I'll show you how that happens in just a moment. And this will actually give you credit for reduced plug loads, which is something many of us in the modeling community have been trying to find out a way to do. So this is equation 4. This would be method 2 or 3. So P is the power density in the space in watts per square foot. PD, power density sub SD, is the estimate of receptacle power from computers, monitors, servers, printers, copy machines, and so forth, which is determined from equation 5. And then these three values, C sub SD, PD, miscellaneous, and D, the diversity factor, are all taken from Appendix B. So these values are given under the plug load section. Here are the values for C, the power density for miscellaneous, and the diversity factor D. These values are all taken from some work that the National Renewable Energy Laboratories did when they calculated they're published in their paper methodology for modeling building energy performance across the commercial sector. So we're indebted to NREL for these values. Equation 5, which feeds into equation 4, is a long equation, but it's a fairly simple equation. It gives you the power density in a space as a function of the number of devices that you count up in the space. So the M factor is the multiplier for credits. For the baseline, this would always be 1, and for method 2, it would always be 1. But for the rated building, this multiplier could be less than 1. N is the number of devices in question, and P is the power associated with each device, which is taken from Table 38 of COMNET. So Table 38 of COMNET was also based on the work from NREL, and this shows the nominal mean power for various devices listed here: personal computers, CRT monitors, LCD monitors, servers, cash registers, laser printers, and so forth. So using that previous equation, you basically multiply the number of personal computers times 55, the number of flat plate computer monitors times 25, and this results in the value of the power density that's calculated for the space. Then moving on to how we handle credits. This table shows the credit that's offered by COMNET for each of the devices. The credit depends on the time period of commitment that the building owner is willing to make towards the purchase of Energy Star equipment. So if the building owner is willing to say, yeah, I will buy nothing but Energy Star computers for for at least 10 years, then the value would be zero point 0.1. The credit basically would be about 12% power reduction. If he's willing to extend that to 30 years, the credit would be about a 25% power reduction. The next table actually converts these into multipliers, which are used in the equation. These values are essentially 1 minus the credit. So you can see by scanning this table that the longer the commitment that the building owner is willing to make, the larger the credit. Now these credits are based on US EPA's goals of and their criteria for establishing Energy Star equipment. We dug into their technical reports and found out the percent savings that they expect to achieve from Energy Star equipment compared to average equipment, and that's what these things are based on. And then we discounted those for shorter time commitments. So moving on to commercial refrigeration is another area where I think we've made some innovations in COMNET. There's several building descriptors. The first building descriptor is the method that's used to model refrigeration, and we recognize three methods. The first method is simply to use the COMNET default values, which are expressed in Appendix B as watts per square foot numbers. The second method, which is similar to method 2 with receptacle loads, if you know what type of equipment you've got in the space, then you can base your estimate of refrigeration power on a count of different types of refrigeration equipment. And then the third method would be to build some sort of explicit refrigeration model, such as what's contained in DOE 2.2, I believe it is, or maybe it's 2.3. It's one of Jeff Hirsch's models that has refrigeration explicitly in there. And there's probably other simulators around that also have explicit refrigeration models. When you get past the modeling method, then refrigeration power would be the input with either method 1 or 2. This would be the total watts of refrigeration. The refrigeration schedule, for the most part, would be assumed to be just 24/7 times 52 weeks. There's and then in some cases, there's a input called remote condensing fraction, which I'll cover in a little more detail in a moment, and the refrigeration COP. Anyway, the basic COMNET defaults are shown in the next to the last column in Appendix B, modeling data, and these are expressed as watts per square foot numbers. These can be used directly, and no further calculations are needed. When you move on to the DOE method, we have some default values for walk-in freezers and refrigerators. These are shown here as watts per square foot numbers. These would be would always be used for the baseline building, and they would be the default for the rated building. These are watts per square foot of actual walk-in refrigerator space or freezer space. Then there's the DOE refrigerated casework table, which is included, and these provide also defaults for the rated building, and they're specified as the input values for the baseline building. There's a lot of codes here, which you have to kind of look down below. HZO, for instance, is a horizontal open refrigerated case. VOP is a vertical open refrigeration case. And the standard power level is specified as a function of the total, either the total display area, TDA, or as the volume. So for instance, if you look at a vertical open refrigeration case, the kilowatt hours per day are 0.82 times the total display area plus 4.07. So these numbers are used in COMNET as defaults. The DOE came out with their refrigeration standards about the time we published the first version of COMNET, so we were able to use these values. The remote condensing fraction, those of you that are familiar with commercial refrigeration know that the condenser can either be located inside or outside. If the condenser is located inside, like is the case with normal refrigerators, then all of the heat that's produced by the compressors results in direct heat gain into the space. When the condensers are located outdoors, which is the case with most supermarkets and some convenience stores, then the commercial refrigeration system actually removes heat from the space and behaves a little like an air conditioner. So what this equation does is it takes into account the remote condensing fraction, F, which is the fraction of condenser heat that's outdoors as opposed to indoors. And then the kW is the total power of the refrigeration system, determined either through the COMNET defaults or from the DOE2 performance rating method. And the COP is the coefficient of performance of the compressor. So you plug those values in, and it gives you the value Q, which is the rate of heat removal from the space, assuming continuous operation of the HVAC system. So this could be plugged back into the model, and you could get a more accurate simulation, even if your model doesn't explicitly deal with commercial refrigeration. The next section deals with elevators, escalators, and moving walkways. There's basically two building descriptors: the power associated with them and the schedule. The machines are assumed to be inside the conditioned space, so they're adding heat to the space. And here are the COMNET defaults. These are given for different modes of operation, whether the elevator or escalator is active, in a ready state, a standby state, or it's off. And there's also typical annual energy use that's given here. So you could create a schedule of the hours that you think the elevators would be active, ready, or in standby mode, and then these power factors would be applied to each section of your schedule. The annual hours are typical annual hours, and these both sum to the 8,760, which are the total hours in a year, a non-leap year. Those are the values for escalators and elevators. We don't have a method yet for crediting reductions in elevator or escalator use, but these values should go into both the baseline and the rated building models so that we get an accurate estimate of total energy use. And then the last one that we're going to cover today is gas use. This would be for cooking mostly in restaurants and maybe some other situations, decorative gas appliances perhaps. The building descriptors include the power, the schedule, the location of the gas equipment, which it's assumed to be indoors unless you specify otherwise, and the radiation factor, which defaults to 0.15, but other values can be used if appropriate. And so the default values for interior gas appliance use are shown in Appendix B, and those can be used as the default, or if you've got more accurate values, you can put those in too. But they're neutral dependent, which means that they apply to both baseline and the rated building. So with that, I'll wrap this section up. I took a little bit longer, but I think this particular section is one of the most important pieces of COMNET. It's one of the areas where we put our greatest effort in, and I think it's one of the areas where we made some innovations. So with that, I'll stop, and Dimitri, you can take questions, and I'll try to answer them.